Welcome back. Let's do another problem. You have a ring here that is kept in place by this neck here, which is on top of this post that itself is secured in the ground. And so you have 3 cables attached to this ring, and these cables themselves are connected to electric motors that can regulate the tension forces in those cables. And these motors as well, they are attached to walls. And so this ring is being pulled by 3 cables in 3 different directions. The ring is being pulled in this direction with a force of 50 newtons, then in this direction with 30 newtons, and in this direction with 20 newtons. So let this force be F1, this one F2, and this one F3. Now it's important to note that the line of actions of all the 3 vectors, they meet in the center of the ring. And that's important because suppose if your ring was here and then one force was like this, then another force like this, but then a third force like this, the line of action of the third force would not go through the center of the ring. That would also make the ring rotate in this direction if this ring was not being held in place somewhere. However, if the line of action of the third force also goes through the center of the circle, then the combination of these 3 forces would not try to make this circle rotate nor in this direction nor in that direction. And now the angle between F2 and this vertical line here, this angle here, that's 20 degrees. Then for F1, instead of an angle, I can in fact represent its direction in a different way. I can draw here a small right triangle, and I can say that this is 4, this is 3, and then this side here, it's 5. It's another way to represent its direction, and if you need some angles for F1, then using trigonometry, you can use this information to obtain the direction of F1 in terms of angles. And then the direction of F3, that's 0 degrees. And now this one here, that's the neck, which holds the circle in place. The question now is the following. Suppose that this neck breaks. Then right at the time when the neck breaks, in which direction will that ring accelerate? What would be the angle of the ring's acceleration vector with respect to this positive x-axis right when the neck breaks? And by the way, here we neglect the force of gravity. So we assume that there is no force of gravity that acts on the ring. Just like force, acceleration is also a vector. It has a magnitude and a direction. The Newton's second law for constant mass is force equals mass times acceleration. F and A, they are vectors. Both of them have a magnitude and a direction. And then mass, that's a scalar, because it only has a magnitude but no direction. Anyway, I would like you to try solving this problem by yourself first, before you see the solutions. However, you might need some more mathematical tools for that. Let me give you them first, and then try solving this problem on your own. Welcome back. Let's now develop some more mathematical tools. First of all, this is very basic and you probably already know it. If I have this random triangle and I multiply A times H, then I get the area of this rectangle. And if I divide it by 2, then I get the area of this subtriangle on the left side. And then I can do the same thing on the right side, B times H. It gives me the area of this rectangle, and then I divide it by 2, and then obviously I get the area of the subtriangle on the right side. That means if you want the area of the entire triangle, you add them up, and that's why this is the formula that you use in order to calculate the area of a triangle. A plus B, which is this one here, times h over 2. But now imagine that I have a square. Each side is divided into A and B parts as shown in the image. Then I connect these points like this. And so I have 4 right triangles here. Both of their sides, A and B, they are equal for all the right triangles. It means that all of them have the same hypotenuse, which is C. They are all equal triangles here. That means that you have a smaller square inside the big square. The area of the smaller square, it's C squared. But it's also the area of the big square minus the areas of the 4 right triangles that you have here. So the area of the big square, that's A plus B squared. And the area of one of those right triangles, well, that's A times B over 2. And so you would agree that the area of the small square, it equals the area of the big square minus 4 times the area of one of those right triangles. So that means that C squared equals A plus B squared minus 4 times A times B over 2. So C squared equals this thing. It can be written like this, A plus B times A plus B. Then here you can take away this 2, and here instead of 4 you will have 2. And so in the end, this one here will be A plus B squared, and then minus 2AB, which is here. Then this term and this term, they get cancelled, and you are left with C squared equals A squared plus B squared. And remember, you had your right triangle. This one was A, this one was B, and this one was C. And so this law is called Pythagoras theorem. It says that if you have a right triangle, then your hypotenuse C, it's related to the other 2 sides like this. C squared equals A squared plus B squared. But now you know where it comes from. And finally, if you have another random triangle, the big ABC letters, they are angles. The small ABC letters, they are the sides of the triangle. Then I can draw another line here, H. It's perpendicular to B. And so if I say that this one is X, then that means that this one is B minus X. Then I can also say cosine A equals X over C, because this is a right triangle here. That's trigonometry. That means that X equals C times cosine A. Using the Pythagoras theorem, I can also say that C squared equals X squared plus H squared. Again, because you have a right triangle here. Then I can use the same rule for this other sub-triangle, which is also a right triangle. I can say that A squared equals B minus X squared plus H squared. Then from this relationship, I can say that H squared equals C squared minus X squared. And now I can take this one here, and I can put it here instead of H squared. So I have A squared equals B minus X squared plus C squared minus X squared. If I write it out, then I will have this expression. I can cancel out the X squared, and now this X here, it will be replaced by this expression here. So this one will come here. And so in that case, I will have A squared equals b squared plus c squared minus 2 times b times c times cosine and then angle A. And that's one important result. And so you can see that when you have your angle A and you know the two sides that come from this angle, so B and C, then you can calculate the side that is opposite to this angle A. And that's what this formula says. You can use similar derivation to obtain this relationship. B squared equals A squared plus C squared minus 2 times A times C times cosine B. Again, you know this angle B, you know this side C and this side A, and then using this formula, you can calculate this side B. And similarly, if you know the angle C and you have the side B and A, then you will have C squared, and the C side is opposite to the angle C, and it equals A squared plus B squared minus 2 times A times B times cosine C. Again, you can obtain this using similar derivation that we have made here. In fact, let this also be your exercise. Try to derive these two relationships. Try to achieve them on your own. I will do that for you as well, but first I want to solve this exercise here, and then I will derive these ones for you. But try it yourself first. And so these three equations, it's called the cosine rule or the cosine law. And so now, as you start trying to solve this exercise on your own first, you might find these three relationships very useful. So I've given you all the necessary math tools that you need in order to conquer this exercise, and I wish you good luck. Thank you very much. Welcome back. Let's now solve this ring exercise. The situation here is that you have a ring that is subjected to these three forces, and the ring was held in one place by this neck. And so if that neck were to break under those forces, then what would be the direction of the ring's acceleration at the moment when the neck breaks? You have to find the angle of that acceleration with respect to the positive x-axis. Well, first of all, why do objects accelerate in the first place? They accelerate because there is imbalance in the forces. When you sum up all the force vectors, then you get a resultant force vector, or in other words, a net force vector. By the way, it's very common to put an arrow on vector symbols to make it very clear that you're dealing with a vector and not with a scalar. And so, the Newton's second law with constant mass states that F net equals mass times acceleration. If F net is not 0 newtons, then an object undergoes acceleration. And that means that this ring will accelerate somewhere if this neck breaks. Another thing is that the direction of F net is the same like the direction of A. And so, in order to solve this problem, we need to find this F net or Fr and its direction, and then acceleration will have the same direction. To find F net, you can use the tools that you have learned so far: the parallelogram law, the law of sines and cosines, etc. Since we have three vectors that we have to add, we can first add, for example, F2 plus F3. That will give us F apostrophe, and then Fr equals F apostrophe plus F1. And so if this neck breaks, then essentially we can forget about everything else and just think in terms of this ring. you have 50 newtons in this direction, 30 newtons in this direction, and 20 newtons in this direction. This is F1, F2, and F3. And so let's first add up F2 and F3. I will again draw the force axis here. They measure newtons in the x and y direction. And so from the origin, I draw F3, which is 50 newtons, and F2, which is 20 newtons. Remember the angle here, it's 20 degrees. And so I'm going to use the parallelogram rule. From the head of 20 newtons, I can draw a line that is parallel to this other vector of 50 newtons. And then from the head of 50 newtons, I can draw another line that is parallel to the one of 20 newtons, like this. And so this is the point where they cross. So essentially, this is your shifted F3 vector, which is 50 newtons, and this is your shifted F2 vector, which is 20 newtons, and the resultant vector is from the origin until this crossing point. So that's your F apostrophe. Now, since we know that this is 20 degrees here, then we also know that this is 20 degrees here. But since you have 90 degrees here, you know that this part here, that's 70 degrees. And so we need to find this F apostrophe, which is the vector magnitude of this resultant vector, and we also need its direction, and let's call it theta. We need to find this theta. As you can see, we have a triangle here. Essentially, this triangle looks like this. And also, what I haven't mentioned yet is that since you have 20 newtons here, then on this side, this is also 20 newtons, because essentially it's the shifted vector. So I have 20 newtons here, and this one here, that's 70 degrees. And now you can use the law that you have just learned. You have this angle, 70 degrees, and you have two sides that come from this angle. And so you can use the cosine rule here. You can write F apostrophe squared equals 20 squared plus 50 squared minus 2 times 20 and 50 times cosine 70 degrees. If I want my F apostrophe, then I can just square root this entire thing, or alternatively I'll just write here to the power of 1/2, then this 2 will disappear, and so from that I know that F apostrophe equals 47.074 newtons. So you know the vector magnitude of F apostrophe. And now you have to find this theta. Well, for that you can use the sine law. You can write F apostrophe over sine 70 degrees, and that equals 20 over sine theta. From that you can say that sine theta equals 20 over F apostrophe times sine 70 degrees. And that means that theta equals inverse sine, and then all this, but you know what your F apostrophe is. It's 47.074 newtons, and so you will have 23.53 degrees. So that's your theta here. And as you can see, it's clockwise. That's the direction of F apostrophe. Welcome back. So now that we have our F apostrophe and theta, now we can calculate FR by adding up F apostrophe and F1. Again, I will draw two axes that measure forces. From the origin, I draw my F apostrophe, which is 47.074 newtons. Then theta was 23.53 degrees. Then this is F1, 30 newtons. We could measure its direction like this. And now, in order to add up these two vectors, from the head of F1, I draw a line that is parallel to F apostrophe, essentially I shift this f apostrophe and put it here along this dotted line. And then I do the same thing with f1. I draw a line parallel to f1. And so these two lines, they meet somewhere here. Essentially, this vector here is the same one like this one here, f1, and this one here, it's this f apostrophe. And you can see that they meet here, in this point, which means that from the origin, I draw this vector, which is my fr. That's what I need to find. And then we also need to find this angle here, this small angle from the positive x-axis. Then we know the direction of the ring's acceleration when the neck breaks. So here we have to do some geometry. First of all, I want to know this angle alpha. It can be calculated very easily. Alpha equals inverse tangent 3/4, and so you get 36.87 degrees. That's this angle. Now if I draw a vertical line here and a horizontal line here, then you have a rectangle here in this second quadrant. So here you can have another side, and then here you can have another side, which means that if you have alpha here, then that means that you also have alpha here. And then you know your theta here, which is 23.53 degrees from the positive x-axis, but since this f apostrophe and then this shifted f apostrophe, this orange line here, since they are parallel to each other, then that means that this angle here, that's also your theta, which is this one, 23.53 degrees. That's because this purple side of the rectangle, it's parallel to this x-axis. And then this orange line, it's parallel to f apostrophe. And now I'm going to define another angle, and I'm going to call this angle phi. And now it's very easy to find phi. Phi equals alpha minus theta, 36.87 degrees, minus 23.53 degrees. That's 13.34 degrees. Now note that even though it doesn't seem like that, but in reality, these two triangles here, they're the same triangles. You have one triangle here, which is the upper one. This is FR. This is 30 newtons. This is 47.074 newtons. You have your phi angle here. And then you have this lower triangle, where again, this is FR. This is 47.074. And this is 30. You saw that from the previous exercise that when you use the parallelogram rule in order to add vectors, you would take one vector and you would shift it here, and then you would take another vector that you have here and you would shift it here, and then the resultant vector would go from the origin to the place where the heads of two shifted vectors meet, and that would give you two equal triangles. And so since you have a phi angle here, and then 30 newtons on one side, and then 47 newtons on the other side, then in this lower triangle, you have 47 newtons here, and 30 newtons here, and since it's the same triangle, because also your FRs here are the same, because of that, this angle here, it's also your phi angle, the same phi angle that you have here. So I can say that this one, that's phi. And you know that angle phi, it's 13.34 degrees. And you also know both sides that come from this angle, 47.074 newtons, and the other one, it's 30 newtons. It's this triangle here. And now using the cosine law, you can very easily calculate FR. You would have FR squared equals 47.074 squared plus 30 squared minus 2 times 47.074 times 30 times cosine 13.34 degrees. And now you square root it. I'm just going to put here to the power of 1/2. And here I will remove 2. And that will give you Fr equals 19.18 newtons. So that's the magnitude of this Fr vector. And now you can very easily calculate this angle here. Let's call it psi. For that you can use the sine law. Essentially we want this angle here, and you know phi, you know Fr, and the other two sides. So the sine law gives you Fr over sine phi, and that equals, you have 30 here, and opposite to that you have psi. So you can write 30 over sine psi. You know that your Fr is 19.18 newtons, and you know that phi is 13.34 degrees. So sine psi equals 30 over Fr times sine phi. And from that you know that psi equals inverse sine 30 over 19.18 times sine 13.34 degrees. And then you close the parenthesis. That means that psi equals 21.15 degrees. But remember, you need this small angle here. Let's call it beta. So it's from the positive x-axis till this Fr vector. But it's easy to calculate because you know your theta, you know your psi. So your beta equals theta minus psi, or 23.53 degrees minus 21.15 degrees. So beta equals 2.38 degrees clockwise, because also theta was clockwise. So I can say that my Fr equals 19.18 newtons. And another way to represent direction could be like this. This is the positive x-axis, and then I represent the direction like this, 2.38 degrees. From this one, you know that it's clockwise. If it had been like this, then it would have been counterclockwise. But that's not the case here. Here you have clockwise. And so since this is your Fr or F net, then that means that when this neck breaks, and you only consider this ring and these three forces, then the net force on this ring will be in this direction, and then here you will have 2.38 degrees clockwise. And so for constant mass, F net equals mass times acceleration, and F net and acceleration, they have the same direction. So this ring will accelerate in the direction of 2.38 degrees clockwise from the positive x-axis. So we have finished this problem. And now in the next video, what I want to do, I want to derive the remaining two parts of the cosine rule. Let's do that in the next video. Thank you very much. Welcome back. Let's now derive the remaining two parts of the cosine rule. We ended up with this result, a squared equals, and then all that. And so we had a random triangle. We had x, b minus x. We had the h. Then we had three big letters, a, b, and c. They were the angles of the triangle. And then the small a, b, and c letters, they were the triangle sides. And the cosine rule essentially told you that you could calculate the side of a triangle if you knew the angle that was opposite to that side and the two sides that would come from that angle. And so I showed you how to obtain this relationship here, where you took cosine A, which was x over c, because this was a right triangle. But now you also have to obtain these two relationships. So what I'm going to do now, I'm going to say that cosine c equals b minus x over a. And that's true because this is a right triangle here. You have your c here, and so b minus x over a, that's cosine c. And then you can rewrite it like this. B minus x equals a times cosine c. And that means that x equals b minus a times cosine c. Then I take this form again, where you had your x, but instead of replacing it with this one, c times cosine a, I'm going to replace it with this one, which is also x. It's just written in a different form. So I will have a squared equals b squared plus c squared minus 2 times b times x. But instead of x, I'm going to write this expression here. So parenthesis, b minus a times cosine c. And now if I open up these parentheses, then I will have this result. Now you can see that you have b squared here and minus 2b squared here. B squared minus 2b squared, that's minus b squared. So I can get rid of this term and I can put a minus sign here. And now what I will do, I will put all these terms on the right side onto the other side of the equation sign except c squared. So I will have c squared equals a squared plus b squared minus 2ab times cosine c. And look, that's your third result. And now we only need to find the second result. In order to find the second result, I have to draw another line here, like this, and this line is perpendicular to this side C. I'll call this line L. And so I'm going to say that this one is y, and that means that this one here, that's c minus y. And so I can say that cosine b equals y over a. And it makes sense because this is a right triangle here. This is your angle b, and this a is the hypotenuse of this right triangle. That means that y equals a times cosine b. Then I can also use Pythagoras theorem here. I can say that a squared equals y squared plus l squared. Or I can say that l squared equals a squared minus y squared. Again, it's a right triangle, so I can use my Pythagoras theorem here. I can also use this theorem here on this other right triangle. I can say that c minus y squared, which is this length squared, plus l squared, which is this side squared, equals b squared, which is this side squared. But this l squared here, I can replace it with this business here. In that case, I will have c minus y squared plus a squared minus y squared, and that would be b squared. In other words, I will have c squared minus 2cy plus y squared plus a squared minus y squared equals b squared. This y squared and minus y squared, they get cancelled out. So you will have b squared equals a squared plus c squared minus 2 times c times y. But this y here, it can be written like this, a times cosine b. And so as a result, you have b squared and then all this. And there you go. This is your second result here. Now you've seen how the entire cosine rule is derived. In the next videos, we'll solve some more problems on this topic. You will be able to apply the tools that you have learned from a different point of view. I might ask you questions differently, but the vector concepts will stay the same. And of course, I highly recommend that you try those problems on your own first and only then watch my solutions. So see you in the next video, and thank you very much.